Madam.
Good evening, Raut sir. Dr. Raut, good evening. Raut sir. Also, it's okay. Naushad sir,
Yes, sir.
shall we start now?
I'm ready. Think so. I can start. I think the participants who.
Hello.
Yeah. Yeah, Raut sir. Hello, how are you?
Fine, sir. Actually,
I just saw you joining, so I said hello.
yes.
Uh, So I think we should start. Dr. Naushad, I think we should start now.
Okay.
Okay. So I welcome Dr. Naushad once again. We had an excellent session from him on Monday about high-speed CMOS digital design. And this is a kind of a demonstration session, LT-SPICE, schematic entry, etc. So a preliminary session kind of thing. But he will take you through the circuit design aspects today, circuit aspects. And then as far as the layout is concerned, that session will be on Friday. The session will be on Friday. Okay. So I welcome Naushad sir here, and whatever you want to discuss, you can discuss. And there are few students also, BTech students from class. They are in third semester right now, and since they are working on LT-SPICE, I asked them to join this batch also. So welcome, sir, and stage you can go ahead.
Thank you, Professor Rathore. and good evening to all the participants. So today we will see a schematic based design entry of digital circuit. So I will stop the video so that it does not interfere with the speed. So okay, let me share my screen. So is my screen visible to all the participants? Rathore sir, is my screen
Yes, sir. Yes, yes, visible.
Okay, so I have created a folder where I have that electric binary. So you can see that we have this electric binary and the release version 9.07, and I have already shared the required supporting softwares for using this electric VLSI design system. So if you have done all that, you can, when you double click on this electric, this will invoke electric and this electric opens like this. You can adjust the windows just with the help of mouse. Now once you have invoked electric, you have to you need to create a library. So you can create a library by going into file and clicking on new library, right? I have already created a library named STTP S.P.I.T. So, and the extension of the library is JE So I have already created library, therefore I will not be creating library again, and I will cancel this step, and rather I will go and open that library that I have created. I created that library this morning. So you have this library here. I will click on it, and so this library opens. I have created some schematic, but I will be doing a fresh schematic before you. So it was just a test schematic that I did this morning. So now in this library, we need to add the circuits. Rathore sir, am I audible? I'm getting some echo.
Sir, yes, you go ahead. No problem.
Okay,
Everything is fine. Everything is fine.
okay. So now you see how we can add a schematic, new schematic to this library. So first of all, you see the library that I had created. This is that library. Now we want to add cell to this library. And those who have used cadence will notice that the flow of electric is very similar to that cadence, of course, with limited capability. So we will go. So once you have this library, initially you need to set preferences for this library. So for example, you can set preferences for this library. So two important preferences are, one is about tools. SPICE, how to integrate LT SPICE with electric, that I have already shared with you. So you will have to make certain settings here. So these I have already made so as to use the SPICE engine, LT SPICE engine for SPICE simulation in electric. So this is one important step that you need to do. And second important step is to select the technology. Select the technology. So you will be selecting this, various technologies are available. So you will select this scalable CMOS, MOSIS CMOS technology, and we know that the default substrate is P type. So you can select, you shall click, select this P substrate process, and we will be using submicron rules, and we will be you can set actually metal layers. There is a limit on 6 metal layers in this tool. However, you know that in modern state of the art technology, there are around 10 metal layers, even more than 10 metal layers. So of course we cannot do that much, but for learning purpose, 6 metal layers are sufficient for even for a bigger circuit. So we will begin with 3 metal layers only, and then we will select second polysilicon layer. So and this analog. So this is one setting. Another setting that we need to do is about the scale. Means we will be using lambda. In terms of lambda, we will be assigning dimensions in terms of lambda. So for this Moses, we can actually select a scale from here. So if I have presently selected it as 100 nanometer or 0.1 micron, because I will be using 180 nanometer technology. Had I decided to use say 0.25 micron technology, I should have selected it to be 125 or nanometer, like that. Means that way you can actually set the scale. So this will actually set the dimensions that you will be mentioning in the schematic. So once you have done these settings, by going into the preferences here, so these settings are now saved for your library. Now we need to add cell. The circuit that we add to library, they are referred to as cell. And a circuit can have a schematic view, can have a layout view, or can have an icon view. So we will actually first add a schematic view to this library. So we will go to this cell and we will select new cell. Now here you can see that you have all the options: schematic, icon, layout. So right now we want to do a schematic and then name of the cell. So I intend to do inverter schematic, because today I will not be doing a complex schematic. Rather, I will be focusing on the commands that we will be using to measure various performance metrics of an inverter, and then we will see how we can do process voltage temperature variation analysis and Monte Carlo simulation. So that will be the focus. Therefore, I will keep this schematic simple. So I have decided to go ahead with the schematic of an inverter. So I will put the name of the schematic here, and I must select this view. So it is a schematic view. When we will do layout, we will select layout view. So right now I will select a schematic view and then I will click OK. Now a blank window opens up. Now right now you don't see any grid, so we can switch on grid. That will actually help in aligning the components. So I will go and click toggle grid. So from Windows you can go and use toggle grid or a shortcut key Control G for switching on or off the grid. If I click it again, the grid is switched off. So I will go ahead with grids on. Now I have got this work window where I will be putting the components and connecting them together. Now I will select this test schematic, and here you can see you have three tabs: component, explorer, layers. So this layer tab we will be using mostly in layout. This explorer basically shows the cells of your library or details of your library, and in components you can see the you can get the components. So this is the component library for creating a schematic view of the cell. So since I want to create a schematic view of a CMOS inverter, so we know that we need a PMOS and NMOS for CMOS inverter. Now here you can see the PMOS. So I will left click on this PMOS and release the mouse button. I will bring my mouse here and again left click. So this will actually place the PMOSFET here. Then again I will go and point my mouse on this NMOSFET symbol. I will left click on it and release the mouse button, and I will bring my cursor here and again I will left click. This will place an NMOSFET here. Okay. Now we have only two components right now and we have vacant space. So if we want to magnify this view or fit this view into this window, we can actually go to window and click fill window. So when you click fill window, you can see a magnified view. of these components. Now I will align these components. So when I bring my cursor on this component, it is highlighted. You can see that. When I bring the mouse here, it is highlighted. To select it, I will bring my mouse here and I will left click. So now it is selected. Okay, now it is selected. Now I can drag it either with the help of mouse button, means by holding the left button of the mouse, click, and then moving my cursor, I can drag it, or I can drag it with the help of arrow key on my keyboard. So now I am doing it with the key on my keyboard. So, okay, let us align this N MOSFET with that. So now it is aligned. Now we know that in an inverter, the drain of the two transistors, they are connected together. So for connecting together, I will do what? I will bring my mouse here on this corner and I will left click. Sorry, I will bring my mouse here and click, yes, left click here, and then I will bring my mouse here and I will right click here. So you can see I have established a connection. Okay, I will do it again. I'm deleting it. I bring my mouse here, then this component gets highlighted. I left click and release the mouse button. Then I bring my cursor here and now I right click on the mouse. So when I right click on the mouse, these two get connected. You can see this, right? Similarly, I have to connect these gates of the two transistors. So I will bring my mouse here, left click and release the mouse button. Then I will bring my mouse here and right click, release the button. This gets connected. You can see that the gate of the two transistors got connected. The drain of the two transistors got connected. Now we need a power supply and a ground for this inverter. So you can locate here, you have a power supply. Again, I will bring my mouse here on this power supply, point on this mouse, point on this ground component, left click, release the mouse button, bring this here, and again left click to place it here. Now this ground is placed. Now I have to connect it. So I will bring my mouse here, left click, release the button, bring your mouse here, right click. It got connected. And with the help of the roller of my mouse, I can actually move it up and down. So I can move it up and down with the help of roller. Now I have to connect power supply. So power supply symbol in electric is this. This is power supply symbol in electric. So I will bring my mouse here, left click. So this gets selected, release the mouse button, bring it here. So actually, and then again left click. So the power supply got placed. Now I have to make a connection. So I will left click here, release the mouse button, bring the mouse here, right click here. It got connected. So now I have connected. Now you can see this schematic is not fitting in this window. So again, you can go to window and fill window. Now it will adjust the size of this schematic so that you can see the full schematic on this window. Now once we have done that, we will connect input and output pins. So we have the pin here. So again, I will bring my cursor up here, left click. This got attached to the cursor. I bring it here, left click here, left click here, it got placed. Now I have to connect these two. So I will bring my mouse here, left click, release the button. I will bring my mouse here, it gets highlighted, right click, it got connected. Again, I need output pin. So again, I will go here, left click, bring it here, again left click, it is placed. Then I will go and left click here, and then I will bring my mouse here and right click here. So now I have connected the input output pins. So one thing that I should have done in the beginning, but let us do that. The sizing of the transistors. Right now, the length and width of this N MOSFET is 2 lambda, 2 lambda. That is 200, and scale we have selected is 100 nanometer. So length is 200 nanometer and width is 200 nanometer. Similarly here, the default length is 200 nanometer, width is 200 nanometer. So now, size these transistors or assign proper sizes to these transistors. So let's say what we we can do, we can actually change or edit object properties by bringing my mouse here, so it gets highlighted. Now when I double click on this thing pops up. When I double click on it, this thing pops up. Now here you can see that the width and length. So length I will leave to 2 only, that is 200 nanometer. Width now I want to make it 500 nanometer, for example. So I will make it 5. And there are other options also that we don't need right now. And the default name of this transistor, instantiation name, when you write a SPICE code, so you write M1, M2, M3 like that. Similarly, the default instantiation name is NMOS at 0. So I click OK. Now you can see that the width of this transistor has changed to 5. Now similarly, the width of this P MOSFET I can change. Again, I will bring my mouse here, double click. Now I want to make it 10, so that the width of P MOSFET to width of N MOSFET ratio is 2. And OK. So now I have changed the width of P MOSFET to 10 and width of N MOSFET to 5. After that, I need to assign or attach SPICE model for this P MOSFET and N MOSFET. If you remember the MOSFET instantiation, when you do textual entry in a SPICE, so you write M1, drain, gate, source, body, and then you write the name of the model, whether it's an N MOSFET, so you write NMOS, whether it's a P MOSFET, so you will write PMOS. So I will assign model, SPICE model to these transistors. So for that, you bring your mouse here, it gets highlighted, you left click, it gets selected. Now you go to tools. And when you go to tools, then you go to SPICE, simulation SPICE, and here you have set SPICE model, set SPICE model. So when I click on set SPICE model, a default name appears here. So now since the name in the model card that we will be using, see, this is the model card that we will be using, and here the name of the MOSFET is NMOS, right? Therefore, we will edit this name of the SPICE model. So when I bring my mouse here, it gets highlighted, and when I double click on it, now it becomes editable, and I will name it as PMOS. Sorry, let's keep it PMOS, capital PMOS. So now we have assigned a SPICE model named PMOS to this transistor. Similarly, select this transistor by left clicking on it and go to tools. From tools, go to simulation and this is SPICE. Then go to set a SPICE model. So this is the default name of a SPICE model. Double click on it and name it as per your requirement. NMOS. So you can actually move it, adjust it. When you bring your mouse here, it gets highlighted. When you left click, it gets selected. Now with the help of mouse or arrow key, you can actually move it up and down. So that's it. You can place it wherever you want. Okay. And this dotted line actually indicates that this model name is associated with this transistor. Fine. So now we have set the SPICE models for both the transistors. So we have brought the required components, we have connected them, we have sized the transistors, and we have assigned the SPICE model name for these two transistors. And you shall remember that these model names must be same as the name here in your model card. The name in the model card must match with the name of the model that you assign to these transistors in the schematic window. Fine. Now the next step is to export ports, right? So we need to create an input port, output port, and supply and ground. So for that, Let's say first we want to create input port. So you bring your mouse on this pin, it gets highlighted, you left click on it, it gets selected. Now you go here, export, and in export, you create export. So once you click create export, now you can see it is asking the name for this port. So I will name it VIN. I will name it VIN. Okay, and this is an input port. So export characteristics, I will go here and I will select input. Okay, so I got this VIN here. Similarly for output port, so I will go bring my mouse here. I will left click, so it is selected. Now I will go to export. Then I will click create export and the name is vout. And this is output port. So I will select output. Okay. So you got a vout here. Now we want to create a export for this power supply. So I will bring my mouse here, left click, it got selected. Then go to export, create export, VDD. Now let's say this is power supply, so you can have a power here, you can see. Okay, so you got this VDD created. Similarly, I want to create export for this code. So I will bring my mouse here, select it by left clicking on it, then go to export, create export and name it ground. Okay, and this is ground. Fine. Okay. So, and you can actually adjust it now. So now we have created this schematic and we have created ports also. Now we need to add the command for this schematic. We need to do simulation, so we need to add command to this schematic. So to add command to this schematic, now we need to go, we will go to this miscellaneous tab here, and in miscellaneous tab, when you left click on this miscellaneous tab, this menu opens. From this menu, you can go to a SPICE code. So we want to actually add a SPICE code to this schematic. So we will click a SPICE code, left click on this SPICE code, and this thing got attached with the mouse. Now I will place it here by left clicking on it. Okay. So after that, since I will be writing multi-line command, so after that, see this now it is not selected. When I bring my mouse here and left click, it got selected. After that, I need to go to edit, properties and object properties. So when I do object properties here, now this window opens up. So I am going to add multiple line SPICE code, therefore I will select multi-line text here. Okay. If I don't select this multi-line text, then your text will be put, all your text will be put in single line only. But I need multi-line command, so I will select this multi-line here. Now I will start adding the SPICE code. So first of all, I need to include the model card. So I will be using the model cards. You see, I have saved, already put this model card, TSMC 180 nanometer model card in my folder. I have already put this. So I need to use this model card, 180 nanometer TSMC model for simulation and analysis. So I will go here and I will actually add the command. So the command for including a model card is dot include. Dot include is the command. And since this model card is in this folder itself, so I need not to specify path. I can simply write TSMC, sorry, the name shall be TSMC 180.txt. It's a text file. Right. So that is the first line of the SPICE command. After that, I will add VDD. Okay, I will add some parameter, for example, dot param supply is equal to 1.8 volt. So this actually parameterize it, and we can change the supply voltage just by changing the value here. So that is why I am using this dot param command. Then I can use VDD, and the node is VDD ground 0 DC, and then I can simply write supply. Then suppose I want to do a DC analysis, or let us go and do the AC analysis directly. So for that, I need to apply V in, and this V in must be applied at the node V in and ground, and I want to apply a pulse input. So you know the format for the pulse input. So format for pulse input is the initial voltage, so it is 0 volt, then 1.8 volt, right? And the delay. So let's say signal delay 1 picosecond, 100 picosecond, then the rise time. So let's say rise time is 10 picoseconds, then the fall time, let's say fall time is 10 picoseconds. Then the pulse width, so let's say pulse width is 200 picoseconds, and then the time period, so time period let's say is 500 picoseconds. So this is how we can assign a pulse input to this inverter. Now I want to do a transient analysis. So dot tran, and then we write say step size 1 picosecond, and we want to run this transient analysis for 2 cycles, for example. So I will run it for say 600 picoseconds, right? So I have added this command. So after that, when I click OK, now you can see that this code is placed here. So you can again go to window and fill window. So you can see this command here. So this SPICE code got added to this cell. Okay. Now I hope we are ready for a SPICE simulation. We will edit this command for measuring various performance parameters. But let us first test, run it, and see that everything is working fine. So let's go to for invoking a SPICE simulation, and a SPICE simulation will be done by LT-SPICE. We have already integrated the LT-SPICE engine with electric for a SPICE simulation. So when I go to tools and to simulate and click on write SPICE det. So now you see this LT-SPICE is invoked, but I am getting some error, and the error is that unknown parameter supply. Okay, let me see what went wrong. Let me again go to this. Okay, let me again exit this, and let me go to this supply. What current supply? Save it, and then again try to invoke the SPICE simulation. Now it's fine. So I forgot actually to put that this parameter. Whenever you use parameter, you put it in single quotes. So I forgot that. Okay. So you can actually rather than writing a 1.8 volt supply here, you can write a supply here also, so that when you do voltage scaling, the input signal is also scaled. Right. So I will again skip this LT-SPICE and again invoke simulation from here. So when I invoke simulation from here, write SPICE there. So you see that LT-SPICE is invoked automatically because we have integrated this LT-SPICE with electric VLSI design system. So electric is basically using LT-SPICE engine for a SPICE simulation. And you can see that this has also extracted the SPICE netlist, we did not write these commands. You can see that this has extracted the SPICE netlist. So you have got the SPICE netlist extracted from that schematic view of the cell. You can see that you have two transistors. So you have two instances of the transistors, and then these are the commands that you have given. So now let us plot the input output waveform and see whether it is giving you the inverter functionality or not. So for plotting, adding waveform to this plot, you shall go here, left click on it, so this window pops up. Now by pressing Control button on the keyboard, I will select V in and V out. Okay, and then I click OK. Now you can see we are getting this waveform, and that actually is the inverter characteristics. So you have the input waveform and you have the output waveform. So you are getting the inverter characteristics through this transient simulation, right? Now, so far it's fine. Now, what we are going to see, so we have actually learned doing the schematic of the inverter and adding a SPICE code to that schematic view of the cell, and we just run the SPICE simulation using LTS SPICE that is invoked from the electric itself, and we have verified that okay, the circuit is working fine, it is working as inverter.
Naushad sir.
Yes,
Naushad sir.
Yes.
If anybody has any question up till now, this is the right time to pause. You have done one transient simulation.
That will be fine. That will be okay. So
या तो अब तक किसी को कोई क्वेश्चन है क्या? एनीबडी हैज एनी? आई थिंक एक मैडम ने, अमृता मैडम ने पूछा है कुछ, तो उनका क्लियर हो गया कि डाउट? आई डोंट नो.
yes, ma'am.
Can you please repeat about adding the text and something like that? उसके बारे में कुछ बता दीजिए. Madam, you can unmute if you can, or if it is clear, it is okay.
Hello, sir.
Yes, please.
Sir, I have a 300 nanometer text file for this electric. Earlier I was using.
No problem.
Sir, now can I get the TSMC 180 nanometer file?
Yeah, of course, I will share it, no issue.
Oh, I'm Jayashree madam from Textile and Engineering Institute. I'll put my mail, sir, here.
Okay, no issue.
Okay, sir, thank you.
Share it.
Sir, one more thing, there is a spike in the output signal.
Yes, that is interesting. It is because of the capacitances that we learned between gate to drain capacitance.
Yes, sir.
It's overshoot and undershoot that you are seeing on the output characteristics. It's because of the coupling of the input and output.
Right, sir, right.
That is gate to drain capacitance of NMOS and PMOS.
So can we eliminate by doing something, sir?
You cannot eliminate it actually because the capacitance is there and therefore it will be there. You can minimize it and it will be actually why it is a significant overshoot and undershoot is there because we have not connected any external load.
Right.
This is a schematic.
Yeah.
We have not connected any external load. So what has happened actually, this coupling capacitance and the parasitic capacitance at the output, they are comparable.
Yes, sir.
They are comparable, and that is why you have a large overshoot and undershoot. Okay, I will connect a capacitor at the output and I will demonstrate that that undershoot and overshoot is actually reduced. So that actually depends on the ratio of this coupling capacitor between input to output and the capacitance at the output node. So, okay, let me connect a capacitor at the output node. So I will bring a mouse here, left click on this capacitor, and I will bring this capacitor here. Okay. So right now the value of the capacitor is 100 millifarads. I will double click on this and I will change it to say femtofarads, and 10 femtofarads will be sufficient, I think. That's the typical value. So 10 femtofarads. Now I will bring another ground, or I can connect this ground from here, left click, right click, so it got connected, left click and right click, so it got connected. So now I have this load capacitor at the output. Now I will skip it from, exit it, and again invoke the SPICE simulation from here. So I will go to tool, simulate SPICE, write SPICE depth. Now I will add the waveform, so I will click on it, and by keeping the control pressed on my keyboard, I will select the two signals that I want to plot, and okay, here it is. Now you can see.
Yeah. Yes, sir.
Now you can see the overshoot and undershoot has reduced.
Yes, sir.
Are you convinced?
Yes, sir. Yes, sir. Definitely.
So that actually the amount of overshoot, undershoot, that depends on the ratio of these capacitors, the coupling capacitor from input to output node and the capacitor connected at the output node and ground. So
Okay.
as you go
Okay.
on increasing the value of this capacitor, that overshoot, undershoot will actually decrease.
Okay, sir. Okay. Thank you.
Okay. So any
Oh.
other query?
No, sir. No. Okay.
Fine. So let's go ahead. So this was till now we have just demonstrated that this circuit is working as an inverter. Now we go ahead and we try to measure the performance parameters of this inverter. For example, for digital circuits, the performance parameters. So we may be interested in measuring the delay of this inverter. We may be interested in measuring the power dissipation of this inverter. And when we talk about the power dissipation, we may be interested in measuring the leakage power and dynamic power. So we can measure both leakage power and dynamic power using commands. And using commands, we can measure PDP or EDP, energy delay product or power delay product. Right. So let us go ahead and see how we can write commands to measure various performance parameters of this inverter. So for that, I will again double click on this SPICE code because I need to edit this SPICE code. So I will double click on it. So now I have this before me. Now I can go ahead and add some commands. So this LTS-SPICE supports dot measure command for making or for measuring various performance parameters. So I will use dot measure, and then first of all, we want to measure the rise fall time of the output waveform. So for measuring you see, you have this waveform, you can see this waveform, you have a falling waveform here, the output is rising here. So if we want to measure the fall time and rise time, we have already seen the signal characteristic and the definition of rise fall time in the previous session. So that definition we will be using for measuring the fall time and rise time of the output signal. So for that, we will add the command measure and then the type of the analysis. So it is transient analysis. So let me first measure the fall time. So I will name it fall time. And then this is a keyword, trigger is keyword. So this fall time is actually the name of the measuring parameter. The parameter we are measuring, we can name it. So this is the name of the parameter. You can give any name. Okay. This tran is keyword and this trigger is again the keyword. So this trigger, and then we want to measure the output. So V for voltage and V out, the name of the output signal. And then what value? So val is equal to, so we have seen that for fall time, it shall be from 90% to 10%. So we will write 0.9 multiplied by supply. So now you can appreciate the importance of defining a parameter supply here. You need not to write the exact value, rather you can simply write supply here. So this is valve. So the measurement will actually be triggered at what point? When the value of the output voltage is 90% of the supply. And it is the first falling waveform. So fall is equal to 1. You can see we are measuring fall time. So this is the first fall. If I had simulated it for a longer time, I will be having multiple fall and rise on the output signal. since I have simulated it for this much time only, so this is the first fall and this is the first rise of the output signal. So that is what it means, fall is equal to 1. Then target. Target is what? This is again the keyword, target. And target is again the same signal V out, right? And what value? So 10%. Value is equal to 0.1 into supply. Okay. So, and then this is also the fall is equal to 1. Okay, let me reduce the text size so that we will be able to see the command. So I will go here and decrease the text size. Actually, I have this control minus. So with control minus, I can decrease the size of the text. So I can put it here. Now, so I have put this command. So I hope it is visible now. I have not reduced the size too much. Is it visible?
Yes, sir, it
Visible,
is
sir.
visible.
Yeah, visible.
Okay. So I have written the command for measuring the fall time of the output signal. For measuring the rise time of the output signal, again I need to add similar command. So to be fast, I will just copy it. Shift and arrow key, I copied it and then I will paste it below. I will paste it here and then edit it. So for measuring rise time, I will name it as rise. I will name it as rise. And then now the trigger, the signal remains same, V out value. Now value will be from 10% to, and this fall will be replaced by rise. These are all keywords. And from 10% to 90%. And this will also be replaced by rise. So this shall measure the rise time. Okay. Now suppose I will separate these by a space so that you can clearly. Now this will actually return the rise time and fall time of the output signal. Now we want to measure the delay. So for measuring the delay, again we want to add similar command. So I will paste the same command and edit. Same measure command and I will edit it. Now I want to measure delay. So T, I will name it, fan will remain there. And then I will name the instance rise time as T underscore HL when the output is going from high to low. Now here you shall notice that what will trigger the measurement. So input signal will trigger the measurement. So when the input has reached to 50%, so when the input has reached to 50%, the measurement will be triggered. And input is actually rising. When the output is falling, input is rising. You can see the input is rising. This input is rising. So I have added this rise is equal to 1 and the target is B out. Okay, fine. And then it is also 50% point and then output is falling. So it's okay. So this will give you high to low delay. Okay. Then I will copy this and paste it and edit to measure low to high delay. So I will copy it and then I will actually paste it here and I will edit it to measure. So for measuring low to high, that is when the output is going from low to high. So again, that measurement will be triggered when the input is at 50%, but the input is now falling. You can see the input is falling. For low to high delay, the input is falling. So here I will write fall. Okay. And this will remain same and the output is rising. So where I will write rise. So this will return TPLH. Okay, to be more TPHL, TPLH. Now, if we want to measure the average delay, so again I will paste that command, but now I will edit it. I will edit it. So dot measure tran, and then I will name it AVG underscore delay, average delay, And here we will be doing some calculation actually. So parameter is equal to, and the delay you know will be given as the sum of TPHL, TP underscore HL plus TP underscore LH divided by 2. So this will return the average delay, right? So let us take a pause here and let us first simulate and see, check whether it is measuring these timing parameters and returning it. How, where can we see these parameters in the output log file? Okay, so we will save it, and again we will. So let me first exit from this instance of SPICE. Again, go to tools, then simulation, SPICE simulation, and then write SPICE dev. So this has done. So input output waveform remains same. That you can see, we have not made any changes there, so that will remain same. Now where can we see these measurement parameters? So for seeing these measurement parameters, actually SPICE saves it in some log file. So we will go here, open, and then select all files. So you can see this inverter SPI, this is the net list, and this inverter actually, this file actually shall have all those parameters. So now you can see those parameters in this output file. You see it returns the fall time is 61 picoseconds, the rise time is 92 picoseconds, and TPHL is 44 picoseconds, TPLH is 58 picoseconds, and the average delay is 51.6 picoseconds. So you can see that by using these commands, you can accurately measure these timing parameters. Is that clear, or do you have any query related to this? Okay, so nobody is asking, so I think it is clear. So let us again skip this SPICE, and now we will add some commands to measure the leakage power, dynamic power for this inverter circuit. Okay, so okay, right. So now come and let us add some more commands, measurement commands to measure the leakage power and dynamic power. So for that, actually, I shall have that waveform with me. So I should not have closed that because I will take the timing from here. So this is it. And let us have that output file open. So that output file is open because we will be using these time actually. We will be using these time, okay, for measuring the dynamic power or leakage power. So that is why let us keep it open. Now you can see that for measuring leakage power, for example, so for inverter, you have leakage power for two cases, when the input is 0 and when the input is 1. So you have a leakage current flowing and that results into leakage power. For dynamic power, you have two situations, when the output is switching from high to low and when the output is switching from low to high. Okay, so let us go ahead and add command to measure the dynamic power, leakage power of this circuit. So I will double click on it and then I will go ahead and add some more commands. So to measure leakage power, I will use the command measure tran, then I leak. I am putting the name of leakage current as I leak. I leak is equal to AVG is the keyword that measures the average current, and then I of VDD. So the average current drawn from supply. So supply is VDD. So average current drawn from supply, and we shall assign time during which it shall measure the average current. So you can see that during this time it is in a static state. So I can give, say, something peak 50 picosecond to 60 picosecond. Similarly, when the input is 1, so I can give 180 picosecond to 240 picosecond. So let us first give it 50 to 60 picosecond, or I can take somewhere here also. So you can take the time where it is in a static state. So 50 to 60 picosecond, okay, I will use. So it will be from is equal to 50 picosecond to 2 is equal to 60 picosecond. So it will actually measure, and since I will be measuring 2 leakage current, so I will put a underscore 0. So I leak 0. When I leak 0 means when the input is 0, how much is the average leakage power drawn from the supply. Similarly, I will measure I leak 1. Control C, and then I will paste it, Control V, and then I leak 1 means the leakage current flowing when the input is 1. So for that, I will use this time. So say 180 to 240 picoseconds. So from 180 picosecond to 240 picoseconds. So this will actually give me the leakage current for when the input is 0, leakage current when the input is 1. Now the average or the leakage power, I forget about that. Now for the average leakage power, I can use dot measure tran param is equal to, so average leakage current, okay, parameter fine. I shall give a name also now. So leakage power, this is the name of the parameter that we are measuring. So leakage power. So leakage power will be given as supply multiplied by I leak 0 plus, sorry, I leak 1 divided by 2. That shall give us the average leakage power. Let us run it and test it. So I will go to the simulate and then write S.P.I.T there. So waveform will remain same. Let us directly go to the output waveform and let us see whether it is reporting those leakage power parameters or not. Yes. So you can see here, when the input is 0, the leakage current is 3.9 picoamperes. This minus sign there is because the polarity of the current. So this S.P.I.T is actually the current drawn from the supply is reported with a minus sign. So you need not to worry for that. So when the input is 0, the leakage current is 3.9 picoseconds, and when the input is 1, the leakage current is 4.4 picoseconds. Fine. So that's it. You have got the leakage current, and then you have got the leakage power also. So you can see that you have got the leakage power. So leakage power is 7.5 picowatts. Now let's go ahead, skip this, exit this instance of LTS-SPICE, and let's go ahead and add command to measure dynamic power. So how can we measure dynamic power? So we can measure dynamic power by measuring the average current drawn from the supply when during this time, from, for example, from this time to, I can fix time somewhere here, and similarly from this time to say this time. Okay, so how much current is drawn from the supply means when the input is switching, during this switching, how much current is drawn from the supply, and that's is actually the switching current. So let's go and add command for measuring switching current. So I will actually copy these three commands, Control C, and then I will paste it here and I will edit it. So now I am measuring I going, okay, when the out I switch, okay, let's say it's 0. Yes, you can put any name, no issue. And then I switch 1. Now I switch 0 and I switch 1 will again measure the average current drawn from the supply when the input is switching. So you have two instances. So one instance I can take this time to this time, for example, when the input is switching. Okay. So when the input is 1 here. So let us take, for example, what is this time? Let me take it as I can actually see it from here. I can see it from here. Input is going from 100 picosecond is the delay. So this is 100 picosecond actually. So it is rising at 100 picoseconds, and say I have to take till 180 picoseconds. So say let's take this 100 to 180 picoseconds. So 100 to 180 picoseconds. 80 picoseconds. Similarly, I will take switch 1. So time, so you see this is 100, this is 120, 110, then this is 210, 210, this is 210. So 210 to, let's say, 420, 210 to 420. So I will take it as 210 to 4. Okay, is it 210? No, it is not 210, rather this is 100, 110 and 310. Sorry, this is 310. 310. That's okay. You can actually measure these times. Fine. So this will actually measure the switching current, that is current drawn from supply during these time intervals. That is when the input and output they are switching. And then I will write it as, name it as dynamic power. So dynamic power parameter supply multiplied by I switch 0, I switch 1 divided by 2. So that will actually give us the dynamic power. So let us again invoke the SPICE simulation from here. Go to this and SPICE deck, and then go to this, open the output file that reports the. So now you can see that you have the switching currents reported here, and the dynamic power is also reported here. So this is the dynamic power, this is the switching current when the input is going from 0 to 1, 1 to 0, and when the input is going from 0 to 1. So you can see these are the currents, switching currents, and using that switching current, we can measure actually the dynamic power. So this is how you can use commands to measure the delay and switching power, leakage power of the MOSFET, right? And you can simply add command like this to multiply the dynamic power with the delay to calculate the PDP, power delay product. So let us not go into that. And so I will take a pause here. Is there any query related to these commands? Is there any query?
Sir, Hello,
Yes.
sir.
Yes,
Do we
please.
have any reference for this, for these commands?
Yeah, you
Measurement.
can find these commands in the help file of LT-SPICE.
Okay, sir. Okay.
Actually, these commands shall be compatible with the SPICE engine that we are using. So we are using LT-SPICE engine for SPICE simulation. So you shall refer to the user manual of LT-SPICE.
Okay, sir. Thank you.
So there you can get these commands. Okay, let us go ahead. Now we want to do the corner simulation. Corner simulation means the transistors that we are using. Right now we are assuming that these transistors, they are ideal and there is no variation in the transistor characteristics, and there are no variations in the operating environment like the supply voltage and the temperature, everything remains fixed. However, practically what happens, there will be process variations that actually affect the device parameters like threshold voltage, and there will be environmental variations like the supply voltage may fluctuate or the temperature may change. So to capture the effect of PVT variations, process voltage temperature variations, we will be using the method suggested in the analog integrated circuit design book by Ken Martin. K. Martin. So K. Martin identifies 5 parameters that we shall use to capture the PVT variations, process voltage variations. Is my screen visible? Do you see the PDF file that I have opened?
Yes, sir. Yes, sir.
Okay, thank you. So that Ken Martin's book suggests that we shall target threshold voltage, oxide thickness, mobility, and bulk junction, that is the bottom junction capacitance, and sidewall junction capacitance. These are the 5 parameters that we shall consider for capturing the process voltage and temperature variations, right? So we need to actually create a model card. Earlier, we used that default model card TSMC 180. So that is the model card that uses nominal parameters and it does not capture any process voltage or temperature variations. Now we can edit this model card in the light of the suggestion of K. Martin, who suggests that we shall target threshold voltage, oxide thickness, mobility, bottom junction capacitance, and sidewall junction capacitance, okay, for capturing the effect of process voltage and temperature variations, right? And in this particular example that we are going to see, so threshold voltage will be varied by plus minus 100 millivolt. But it is not necessary that you always vary it by some magnitude. You can also vary it by certain percentage. Okay, so that you can easily do, but just for demonstration purpose, we will be varying the threshold voltage by 100 millivolt. Similarly, oxide thickness is varied from 0.95 times to 1.05 times. So it is actually plus minus 5% variation in the oxide thickness. Similarly, mobility is varied by this much amount, right? And junction capacitance is also varied by plus minus 5%, and sidewall capacitance is also varied by plus minus 5%. Okay, so these are the 5 parameters that has been identified to capture the PVT variations, right? And how we can edit the model card for capturing PVT variations, that has been suggested here. So for N MOSFET, what we will do, see these VT naught, TOX, U naught, CJ and CJSW, these are the model parameters in the nominal model cards. This is the nominal model card. Okay, let me magnify it. So do you see the model card now on my screen? Somebody shall confirm
Yes,
that
sir.
it is.
Yes, sir.
So you can see that right now the oxide thickness Tox, VTH naught, U naught, and CJ and CJSW will be somewhere here. CJ and CJSW, they are all having some nominal values, right? Now we actually need to edit this model card to capture the effect of process and voltage parameters. So now I will do it before you, so we can edit this for capturing the effect of process and voltage parameters. So I will do it before you. So I have seen in the folder, actually you can see, I have already saved this as another model card, TSMC180 PVT. I have saved this same as this, another copy of this TSMC180 PVT. So now I will open it. This is already open actually. This is already open. So this is here. So let me magnify it. So what I have done this afternoon, I have already made those changes for the N MOSFET. So you can see that I have made TOX, I have made these changes, and I have added this parameter SN. So SN is actually S means speed and N is for N MOSFET. So SN is the speed parameter for N MOSFET. And the value of Sn varies from -1 to 1. So when it is -1, it means slow NMOS. And when it is +1, it means fast NMOS. Okay. So these expressions have been edited accordingly. So you can see that VTH naught has also been edited. Similarly, you can see that U naught has also been edited. And then you can see that CJ and CJSW has also been edited in accordance with the suggestion of Kenneth Martin's book. Now I will edit the parameter of PMOS before you. So you have this TOX here. So I will edit it before you. So this shall be TOX divided by 1 plus SP. Now I will write SP. So speed parameter for P MOSFET, and so this I have edited it. So I have actually parameterized it. Now I will edit the threshold voltage parameter of P MOSFET. So this shall be this thing plus SP divided by 10. So now I shall locate that U naught. So U naught is here. So I shall edit it U naught. U naught shall be edited to multiplied by 1 plus SP divided by 20, and then this is square of it. So I have edited this, then I shall locate CJ of P MOSFET. So yeah, here it is, CJ. So CJ I will edit as per the reference book. So I will make it 1 plus SP divided by 20. Right. Okay. Then similarly, I will edit CJSW. So CJSW is 1 plus SP divided by 20. Yeah. So I have edited these 5 parameters to capture the effect of PVT variations. Okay, let me minimize. Now what I will do, now I will go to the schematic view of this, and now we will include PVT variation model card. This model card was the nominal model card. Now we want to include that PVT model card. So I will change it PVT model card. So I have added the PVT model card that we have just created for the simulation of PVT variations, right? And now we will add some more commands to capture the effect of PVT variations. So what we can do actually, we will add some commands. So let's add those commands at towards the end. So that command is dot step command, dot step, then parameter Sn. So Sn I want to vary from -1 to 1 in the steps of 1. So what it will do, it will actually vary the speed parameter of N MOSFET from -1 to 1. So first it will be -1 means slow NMOS, then it will become 0 that is nominal, and then it will become 1 that is fast NMOS. Similarly, I will add a step command around SP -1, 1 and 1. So again, -1 when the SP is -1, PMOS, slow PMOS, then 0 nominal PMOS and 1 fast PMOS. Right? So once we do this, it will now do the simulation by varying Sn and Sp for all the possible conditions, combinations. So let us go and let us exit from this SPICE instance. Exit from this SPICE instance, and let us invoke SPICE simulation again. So let us go simulate write SPICE there, and the output waveform will not waveform. Okay, let us see waveform will also, we will have multiple waveforms we shall have, because we have changed the slow and most here. Now here you can see, here you can see that you have fast NMOS, nominal NMOS, slow NMOS. Okay, similarly, you have fast PMOS, nominal PMOS, slow PMOS. So you can see that you have got the simulations, and let us see the output file, how it has reported those measurement parameters for different combinations of speed parameters. So now you can see how it has varied, the speed parameters of N MOSFET and P MOSFET. So first, -1, so what it means, slow N, slow P, or SS. Okay, nominal N and slow P, fast N, slow P. Then you have slow N, nominal P. Is it visible or shall I magnify?
Is visible.
Okay. Nominal N, nominal P. Then you have fast N, nominal P, slow N, fast P, nominal N, fast P, fast N, fast P. So you can see that you have different steps. Now you can see that all the fall times. So you have how many combinations? 1, 2, 3, 4, 5, 6, 7, 8, 9 combinations. And you have the values reported for all the 9 combinations. Can you see that? So fall time, how the fall time changes. Similarly, the rise time, how the rise time changes for different combinations of transistors means. Similarly, you have the delay, high to low delay, low to high delay, and similarly you have the average delay, how the average delay changes. Similarly, you have the I leak 0, I leak 1, then leakage power. So all those measurement parameters have been reported for different corners. Do you agree? So these actually represent, these steps, these actually represent corners. Okay, so you have both slow, here you have both fast, here you have both nominal, typical, and then you have typical, slow, fast, slow, typical, and like that. Is it clear?
Yes, sir.
Is there any query? If you have any query, please ask.
So the plots are corresponding to the highest and the minimum values in these tables.
Yes. Are you asking that here we are seeing 9 values and here we are seeing only 3 values? Is that
Yeah,
what you are asking?
yeah, correspond. Yeah.
Fine. That is good. That is that's a good
That
observation.
is for the fast it will be the lowest, and for the slow it will be the highest
That
value
is,
from the tables.
good observation actually. Now you see, when we are seeing this fall, so this fall of the output is responsible only because of N MOSFET. Huh?
Yes.
It is because of N MOSFET.
Yes.
So P MOSFET is not playing a role here, means significant role here. So what are the 3 possibilities of N MOSFET? The fast N MOSFET, typical N MOSFET, and slow N MOSFET. Similarly, this rise of the output, so this corresponds to 3 possibilities of P MOSFET. Slow P MOSFET, typical P MOSFET, fast P MOSFET. Do you agree? Do you agree?
Yes, sir.
So shall I go ahead?
Yes.
So this is how we can do corner analysis by defining a speed parameter. There are various other techniques to do the corner analysis, but this technique I really like. This is easy actually, and this is very elaborate, and means we can easily understand that how the parameters have been selected to capture the effect of temperature, voltage, and process variations. Because you see, your threshold voltage will be affected by the temperature and the process variation. Oxide thickness will be affected by the process variation. Mobility will be affected by temperature, process variation, and to some extent supply voltage, of course. Similarly, the junction capacitances, they will be affected by the process variation and the temperature and the voltage also, because they are reverse bias junctions. So these are the parameters that are used to capture the effect of process voltage and temperature variations. And using this kind of command, we can do the corner analysis. Now we are going to see how we can do Monte Carlo simulation. Monte Carlo simulation is another statistical method. Statistical method to analyze the circuit. Right. So for doing Monte Carlo analysis, we again need to make some changes in this netlist. So for Monte Carlo analysis, actually, we need to specify the statistical variation in these parameters, and for that we will make some changes here. So rather than dot step, we will use dot param, and then Sn will be varied. Let's say Sn is varied by flat. Let me see the command. With we can actually assign the distribution how Sn is varied. So we can actually vary Sn by, let me see the command. It is, yes, dot param Sn is equal to flat. Then I will write 1 here. So what it will do actually, that Sn will be varied from -1 to 1 with a uniform distribution. Okay, similarly for P MOSFET, I will use dot param command. I can also use Gaussian variation, but let us take this one example. Flat, and I write 1 here. So this SP will be also varied from -1 to 1, in the range of -1 to 1, and then we will have to assign how many simulations we need to perform, because Monte Carlo simulation, so sample size, what shall be the sample size? So for that I will use the command .step param, and n gives the number of samples. So suppose I want to do 100 samples, 100 simulations. So that is the command, and it shall be .step. I forgot to put a dot here, so .step. So this is the command for Monte Carlo simulation. .step param n is equal to n varies from 1 to 100. So actually it will simulate this net list. The SPICE will simulate this net list for 100 times, and every time this SN and SP is encountered, it will assign a random value in the range of -1 to 1. Okay, so it could be any value between -1 to 1. Similarly, whenever this SP is encountered, our simulator will assign a random value to SP from -1 to 1. Right? And now we will do this. Actually here we define the number of samples, okay, a number of the simulations that it will perform. So that's it. We have edited the netlist, and let's go and invoke the SPICE simulation. So, and it will take some time. Now the SPICE simulation will take some time. I am exiting from this instance of SPICE, and I will go to tools, then simulate and write a SPICE simulation. Now it is taking some time. You can see the now simulation is complete. So it was only 100 simulations. That is why it got completed in few seconds. But normally when you do Monte Carlo simulations, the sample size is really large, 5,000 or 10,000 samples. And then it will take significant amount of time to complete the simulation. So now let us see the plot for input and output for this Monte Carlo simulation. Now you can see that you have 100 waveforms for this. So it is not visible actually. This is, I will try to magnify it. Maybe it is not visible because it is 100 simulations. Okay. So if I reduce the sample size, so this I will reduce so that you can see it. But this actually shows you the variation. Okay. So you can see this shows you the variation. And let us first inspect the output file also. So let us go to this and open it. Now you can see you have the steps listed over here. And sorry. Yeah. So step listed. Now you can see. Now you can see that you have fall time measured for 100 simulations. 100 simulations. You can see 100 simulations. Similarly, rise time measured for 100 simulations. So this is for statistical analysis. You will be performing Monte Carlo simulation, and I have taken a small sample size here. 100 sample size will not be acceptable if you are writing research paper. There they will ask you to simulate or take the sample size of 5,000 or 10,000, and that will take significant time. And to show this variations in the rise fall time, actually I will do what? I will reduce the sample size so that we can see that. So I will make the sample size to 30 so that we can see something there. Then I will go to SPICE and write SPICE there. And now when I plot, this time I will plot V out only. So let us plot V out. Now you can see for 30 simulations, now you can see that you have different input output, different rise fall times for this small simulation. So this is a statistical analysis. This way you can do a statistical analysis. And if you want to, okay, yeah, okay. If you, what actually I wanted to say that if you want to plot this or want to process this data using some other tools, so you may be using some statistical analysis tools for processing the data, because much of the statistical analysis tools are not available in LTS-SPICE so far as I know. In HS-SPICE, you have the statistical analysis commands or tools available, but in LTS-SPICE it is not there. So at times you may need this data to be processed by some other tools. So in that case, what you can do actually, you can extract, you can actually save, export this data as text. So I want to export this V out, so I can export this V out as inverted text. And then I will go to that if this is that, and then when I open it using I can open it using Excel, for example, Excel, and then I can open that. You may use Excel as for data post processing of the data, right? So I will go there on the desktop, STTP, all files, inverter. Okay, I think it was not processed properly. Okay, let me do it again. It was not exported properly. I think I shall do what, export data set, and I shall change this name. Actually, there is a conflict. So data, and then I will click OK. Now I shall have this there, open. Now I shall have, yeah, I have this data now. Open, next, finish. Now you can see that I have that waveform here, and you can actually plot this waveform, and then you can actually insert line. So you can plot it here also. So this way you can actually export the data to Excel or any format. So you have this time versus the out plot here. I should be able to plot this. Why I have not plot this? Let me try to do it again. Okay. Yeah. So I shall be able to plot this line to the scatter plot. Okay, scatter plot, and then I shall do I think I'm making some mistake in plotting it in Excel. But anyway, you have seen that you can actually export this data, and then you can use post processing using Excel or some other tool, post processing tool. So that was about the Monte Carlo simulation. Fine. So I think this is what I planned for today. Now I would like to answer your queries. If you have any query related to this electric VLSI design system for creating cell view and adding command to this tool, and doing the analysis.
So the title of the N. Martin's book.
Okay, title of the Martin's book. Okay, let me type it in the chat box. Okay. Type in the chat box. Wants and then so this is the title of the book. Any other query?
Anybody has any query?
Hello, sir. From okay, sorry.
Hello, please.
How far these electric results are accepted in reputed journals?
See, the results that we are getting those results from LT SPICE, not from electric, because the SPICE includes LT SPICE.
Yes.
Actually, whatever analysis, one thing I shall make clear, maybe some of you may be having doubt that these simulations, these commands we can write in LT SPICE and we can directly actually use only LT SPICE and do the simulation. You are right. For now, whatever we have done, the simulations that we have done, we do not essentially need electric. But I decided to use electric. I decided to go through electric path because in the next session, we will be learning about layouts. And there, schematic and layout that must be done in electric to follow the design flow. If you recall the custom design flows, so the design entry is schematic based. You do the schematic design entry, then you do the pre-layout simulation. So what we have done right now is pre-layout simulation. The next step would be post-layout simulation, that we will do the layout. And after doing the layout, we will be doing DRC, LVS, right?
Yes,
So
sir.
LVS, DRC, all that will be done. And then post-layout simulation will be done. So for those
Yes, sir.
things, we have to use electric. And that is why we have gone through electric route. I have started through electric only. Now your question is that how much these results are accepted. So I shall tell you that LTS Spice is widely used tool and it supports the great advantage of LTS Spice is it is open source and it supports
Yes.
BC4 model. Your PS Spice will not support BC4 model, but LTS Spice supports BC4 model. Okay.
Yes.
And I have compared the results of LTS Spice and HS Spice. They are not very far apart and it is well
Okay.
accepted. And LTS Spice is coming from authentic source. So
Okay.
there is no question about the reliability of LTS Spice.
Okay. Okay, sir. Thank you so much. Thank you.
Sir, I have first of all, let me thank you literally, because this was a really wonderful session. I got everything out of it, sir. But somewhere in while having that hands-on, I got stuck up when that 180 nanometer text file TSMC point was there. I have left my hands on at that particular point and carried out with your explanations there because I was not able to get that file. From where can we get that file, sir?
Okay, I will share it with you. That is available. You can go
Sir,
to Professor Nagendra Krishnapura's website. Do you know
Nagendra
Professor Nagendra
Krishnapura.
Krishnapura, IIT Madras?
Okay, sir.
You can go to his website. Okay, let me open that website, show you. It's available there.
Okay, sir, I'll go through Nagendra Krishnapura sir's website. I'll go through, and from that one,
Yeah, and you
I
can find
required to
all those
download.
model cards there. No issue.
Okay, okay, sir. Thank you for such a nice session, sir. Once again.
My pleasure, my pleasure.
Dipti ma'am, 180 nanometer, you will easily get, you simply Google out, you will get it at many places. 180 nanometer is not the issue now. Okay.
Yeah, you can use it
Okay,
to
sir.
PIT also, predictive
Yeah,
technology.
yeah, you can use
Okay, sir.
PTC.
I'll try.
Yeah, yeah.
Okay, I'll try it out, sir.
Somebody's,
Yeah, this is Khade sir from Pune.
yeah, sir, please go ahead.
Sir, if I want to do a Monte Carlo simulation using this
Yes.
STTP1, because whenever we are going for the Monte Carlo simulation, so is it possible to do the Monte Carlo simulation using this?
We just did Monte Carlo simulation, na?
No, for a specific, yeah, no, means what I am saying in terms of that, what we have got the waveforms, but when we gone through the standard paper, they are having
Samples,
some of
Gaussian, Gaussian kind of distribution.
yeah,
Okay,
Gaussian distribution.
you may be talking about the histogram and all.
Yes,
Yes,
yes. I think he's asking that.
Histogram.
yes,
Yeah.
yes, yes.
So that is what I said. Since those statistical tools are not available, so far as I know, in this LTS-SPICE wave view. So what you can do actually, see, you have those parameters na, in the output file. Those parameters are reported in the output file na, as a
Okay.
text. So you can take these parameters from here, okay, and you can actually use it using some statistical analysis tool. This can be copied, pasted as a text file, and then you can open it in Excel and other statistical tool, and you can do the post processing.
Okay. Yeah.
Actually, we are getting this free tool, so there are some limitations.
Yeah,
And
yeah.
to be frank, there may be some statistical analysis command for LTS-SPICE. It is possible that I may not be aware because mostly I use HSPICE. But for this session, I decided to go ahead with open source tools so that all the participants can practice actually if they wish.
Yeah. Thank you, sir. But sir, wonderful session, sir.
Thank you very much.
Because
Hello, sir.
many times we are not able to get this kind of simulations.
Hello, sir.
Hello.
Hello, sir. The results what we get for all the outputs, are they comparable with Cadence, sir? How much they are near to Cadence tool?
To be frank, I have not compared it with Cadence. Okay, but with HSPICE, I can say that it is comparable.
Okay.
So again, actually, you are doubtful about the acceptability of the results generated by LTS-SPICE.
Yeah.
So
Yes, sir. Yes.
I shall tell you and assure you that
Huh.
there will never be any issue, or I don't think any reviewer will ever raise an issue about the results generated by LTS-SPICE.
Okay, sir. Okay.
That will not be an issue.
Okay, sir. Thank you.
Madam, LTS-SPICE is given by the analog devices. It's a multinational company. No, you just from where you get. You don't get from random sources. It's coming from analog devices. So
Yes, sir.
they are well accepted. The problem with LTS-SPICE is the integration with many tools. That's not available. So you have to rely on probably on multiple tools. That could be an issue. Hi, madam.
Rathod sir,
Okay.
Rathod sir, I'm
Hi,
Ketan
madam.
Raut. Shall I speak just little
Yeah,
few
sir.
words I want to say?
Please go ahead, sir.
Just I want to clarify the madam's doubt. No reviewer or no journal ask which tool you have used for simulation. Even if we refer the good paper, so nowhere written it is simulated using Cadence or Synopsys.
Okay.
Okay.
So that's my opinion. So no one will ask you which tool you have used, and even we don't mention in the paper ki I have used Cadence. We refer the technology. Yes, I have used this low power 45 nanometer technology, TSMC technology, or so. But we don't mention Cadence use or Synopsys use.
Okay, okay.
Okay, so that's my
Yeah,
opinion.
that is. No, it is correct, sir. Correct. You're right.
Okay, sir. Thank you.
Okay.
Modeling and concept.
Anybody has any other doubt or anything?
I think I am bad at time management.
No, no, sir. Yeah, in fact, you did it in the right time. No problem. Sir, there is a command for Monte Carlo. I think that is a .mc or something like that. We can do the Monte Carlo analysis also. But
We
I
are
also
doing
never.
Monte Carlo.
Yeah, but we have not experienced. We never did it. But there are some commands for Monte Carlo, like
Yeah, there
.mc
is.
or something like that.
There
Yeah,
is
there are.
actually that depends on how we are varying. If we are varying certain parameters by some percentage,
Yeah.
so that also we can use. I agree with you. Fully agree with you.
Yes.
And there
Yes,
are other
yes.
commands also for Monte Carlo simulation.
Yes, yes. The Gaussian distribution or something like that.
Yes,
I
yes.
did
And
in
I have
past.
used
It is
a
there.
uniform distribution, flat.
Yes.
So I have used a uniform distribution, but there are other commands also.
Yes, yes. So, but since these things are not regularly used, so we forget about it. Otherwise, there are commands we can actually.
Yes,
go
yes.
with.
So anybody
Yes, yes.
interested can refer to the user manual of S.P.I.T
Yes.
and get the help from there.
Anyone else who would like to ask anything? I don't think so. Very nice. Naushad sir, thank you very much.
It's
Very
my
good
pleasure,
question.
sir.
The people are speaking how the session was, so I need not say anything else now. But because of this session, I have changed my assessment method. For participants, please note. मेरा एग्जाम चेंज हो गया अभी एग्जाम पैटर्न मैंने चेंज कर दिया आप लोगों का सो कल का एग्जाम क्विज नहीं होगा we will not have quiz on spot decision because let us forget about quiz. I am giving you 2 days for simulating this inverter. Whatever sir has shown, you have to do this much. यही करना है आपको. एक LT स्पाइस करना है, उसमें एक CMOS इन्वर्टर का ही सर्किट सिमुलेट करना है, लेकिन उसमें हमको ये दिखना चाहिए, लीकेज का भी दिखना चाहिए और एनालिसिस, पावर एनालिसिस और डिले का भी एनालिसिस दिखना चाहिए. So I will create on a Moodle. I will delete that quiz, which is I had already created questions. I will delete those. I will create an assignment, and you are supposed to submit, do the submission of assignment. मुझे सिर्फ और सिर्फ इसमें से एक फाइल में आपका जिप करके जिसमें ये सिमुलेशन किया हुआ रिजल्ट लगेगा और कुछ नहीं लगेगा. I think that will be good. And if you are not comfortable, किसी का LT Spice का कुछ problems हो रहा है और don't like LT circuit simulation, you like Verilog simulation, I am giving that option also. Either you go for a circuit simulation or you go for a Verilog simulation. But in Verilog simulation, let us decide something which will be a fruitful that kind of circuit, or I leave it to you. A good design which you can submit and which you can show in that showcase in that case.
But sir, for that you have to share this video to us.
Sir, it will be immediately available on channel. I will put here again a channel link.
Okay, sir.
Morning session, there was some kind of technical, I think that happened from my side only because I have to switch on so many things. So I probably forgot to keep just turn on something and therefore the recording was not there. But I have uploaded that also. That record also means morning session का record भी upload किया है. And the channel का link मैं अभी आपको एक सेकंड में you can get all the record sessions over there. Okay.
Yes,
so,
sir. Yes.
Right now itself, and I feel that will be more valuable. This will be more valuable. And one more thing, if you have any problems, Naushad sir will be back on Friday evening, so it will be good for you.
Sir,
sir.
That is what I am saying. If any participant is ready with his or her query, can share the screen and share the problem or difficulty that he or she is facing.
On
So-
Saturday? On Friday?
Right now also, if some participant is ready,
Yeah.
also I can entertain and I can see and I can help.
Yes.
So if there is anybody who wants to share the screen
I-
and tell us the problem that he or she is facing with this electric and LT SPICE thing, so you can share your screen and
but I don't know Shaila madam का problem क्या रहेगा. Madam, you got installed or still there is an issue?
No, sir, there seems to be some problem with softwares related with Linux, perhaps.
Acha.
Yeah, it's giving error, and even to my student, the similar error came on her laptop also. So I'm not sure. I will try to see something through Xilinx or Verilog.
No, madam, I have want your problem to be solved. That's it.
I think we'll do it later on, perhaps.
No,
At present, I don't want to disturb my
Okay.
laptop. Let it work. Yeah. So I had to go to the HP, perhaps dealer. HP representative. They are telling me that show you a problem to HP representative. So I may have to.
Madam, I will show you. In that case, I will show you if anybody, including you, have a problem in installing LT Spice or anything, or including Verilog, I will show you a methodology. Let us say for 10-15 minutes, if I get a time at any point of time tomorrow.
No, that methodology is there. No,
Verilog tool, how to access online and how to do the simulations. You don't require any simulator also.
Okay.
I will show you how to access using online methods. No software is required for that.
Okay, sir.
Verilog simulation. Verilog I will show.
Okay, sir. Okay, that is fine.
Okay.
That is fine.
Yeah. So you need not worry. But then others, those who don't have tool issue, that is perfectly okay. Pandemic situation, so we can agree. But then I believe that others will be able to do the simulation and show what Naushad sir has said. And you should come up with the challenges on Friday. अगर आपको कुछ भी problem है तो, ठीक है? And in that case, let me relax you from both the quizzes. कल का भी हम लोग क्विज नहीं लेते, परसों का भी नहीं लेते, चलेगा मुझे कोई प्रॉब्लम नहीं, लेकिन आपको इसका एक्सपीरियंस आना चाहिए, ठीक है? और दोनों का 20 मार्क, हाँ दोनों का 20 मार्क टोटल, 10+10 20 मार्क्स. ओके, चलेगा, ठीक है. So very nice. Then it's over. If it is over, the session is over. Thank you, Naushad sir. Thank you very much. We'll meet again on Friday.
Thank you,
sir.
Yes.
Mail ID of Naushad sir.
Naushad sir. Sir, email ID. Chat box.
Okay, I will put it in the chat box.
Thank you.
It's Naushad at gmail.com.